screwy thing on this computer, which is actually on this slide slightly problematic. Okay, let me see if I can do what I can here. Okay, so what we are expecting now is a little bit of an extension of what I was just talking about. But now we're going to talk about two events happening in a certain observer's reference frame and ask the question how the time interval between those two events might look for observers in two differently moving reference frames. So what turns out to be the punchline is here, that if I have two events measured by an observer in a certain reference frame, the observer who's in a reference frame that is not moving as defined by that person is going to observe a certain time interval, but the time interval between those same two events measured by somebody in a moving reference frame will be different, okay? And so in fact, the sort of shorthand way of describing this is that moving clocks tick more slowly than clocks at rest. Okay, so moving clocks tick more slowly than clocks at rest. What does a clock move or a clock ticking more slowly imply? It sort of implies that if you're measuring the time between two events and your clock is going slow, you will actually measure a shorter time interval because your clocks are going slow, right? These days, not many of us have mechanical watches, but it used to be that you would have mechanical watches that you wound up, and early on, after you wound them up, they'd be going at a certain calibrated time, but once the mechanism with the wound up, whatever, wound down, your clock would go more slowly. So if your clock is going more slowly, the time interval is actually measured as shorter than it is compared to, let's say, a regular working clock. So this is the idea that time is dilated, stretched out in a moving reference system. So this is where I'm going to get into trouble because an important factor is not really showing up here. The amount by which this time is stretched or dilated is something called the Lorentz factor. This is supposed to be represented by a little symbol of gamma, as you see it is down here. So this is the first introduction of this Lorentz factor or gamma factor, and it's going to appear throughout special relativity. So let's quickly take a look at how it's defined. So this is supposed to be gamma, and gamma, as you can see from this equation, is simply 1 over 1 minus v squared over c squared, okay? C squared being the speed of light in vacuum, and v is the velocity at which my reference frame happens to be moving, okay? So just take a look at the form of this gamma factor or Lorentz factor, and look at two things. First off, the form, 1 over 1 minus v squared over c squared, and if you can, in your head, think about what this looks like as v goes from 0 and approaches the speed of light. Okay, so what form does it have? But then also just keep in mind that there are squares here, and keep in mind that the speed of light is a large number. And you can imagine that this gamma factor only becomes appreciably different from 1 as your speeds become really substantially large fractions of the speed of light. Okay? I haven't, and I should have shown you a figure of this in my notes here in class, but take a look in your textbook and you'll see how this gamma factor varies as a function of speed, v. And again, keep in mind that the big effects come as you're getting very close to the speed of light. So that's an indication of why Newtonian mechanics is so good for most of our daily experiences, because we're very, very far away from situations where the speeds are moving close to the speed of light. But here's the gamma factor. Now, I'm going slower than I expected. I should make a terrible pun there, but I'm not going to. Here is actually the thought experiment that Einstein did that allowed him to determine what this gamma factor would be. And I'm going to move a little bit quickly here because I want to try and get through a couple of things before we wrap up at 11:25. But the thought experiment Einstein did is the following. Now, Einstein did not know about lasers, so that's a little bit of a cheat, but it's a light source. It's still in a moving train car, this blue thing again. And the light source is on the bottom of the interior of the moving train car. It's going to fire a ray of light, a beam of light, a wave of light, depending on your perspective, up from the bottom to the top. It's going to bounce off a mirror on the ceiling in the moving train car, and then it's going to come back down to the bottom where it's going to be detected. So we're going to look at this from a couple of perspectives. They're geometrical, essentially, both from the point of view of an observer inside the moving train car and an observer outside the moving train car. Look at what the path the light travels looks like from both perspectives, and then basically just use Pythagorean theorem to say something about the time travel. So just take a look at this. Maybe this is a cartoon, I can't remember. It is. Okay, so there's the light bouncing down and up from the vantage point of an observer inside the moving train car. So inside the moving train car, everything is just going up and down. So in fact, the time travel for the light in this moving reference frame, delta t, standard notation, a time elapsed between two events, is the distance traveled divided by the speed. Okay, so this is really straightforward in the the moving observer reference frame. The time elapsed is just 2d over c. Now I'm looking from the outside, and I'm going to do this cartoon quickly, and again I'm a little bit hampered by the screwy font rendering on this computer. But now I'm going to imagine looking from the outside. Let me show you this a couple of times. Just focus on that moving train car. This is what it looks like from the outside. Remember, the train car is moving to the right at constant speed, so the light seems to look like this. Okay? All right, so if that's true, you can build the geometrical construct, and again, apologies for the rectangles, which is supposed to be something else, deltas in this case. Wow, this is really messed up. Now I see time with envelopes and files and folders. This is really messed up. I will post this having rendered it correctly when I post it online. Anyway, look at the geometry of that triangle. And you're basically looking at this in terms of distances in the triangle and applying Pythagoras theorem. Everything in the white box is correct. There's no format screw-ups there. But what you actually see, interestingly enough, is where the gamma factor, the Lorentz factor, comes from. Okay? And this is a beautifully simple idea just based on looking at this from two different perspectives, the constancy and the speed of light. Let's look at what the time elapsed looks like from the perspective of the inside observer versus the outside observer. And the important result that drops out is this. So the time difference in the non-moving reference frame is gamma, our Lorentz factor, and here's where it comes from, times the time elapsed in the moving reference frame. Okay? Now think of what this implies. Gamma is bigger than 1 in this case. And so that means if this is bigger than 1, this is smaller than 1. So in that sense, the moving clock is measuring and dilated or kind of slowed down or smaller time interval. So make sure you've got thinking about that the right way around. And this shows us that in fact, time in moving reference frames seems to tick more slowly. All right. So again, I'm seeing horrible examples of font misrenderings here. My apologies. Quick example of this in real life. Just a kind of fun one. Anyone, well, here's the answer. Anyone heard of cosmic rays? Yeah, okay. So cosmic rays have been known about for more than a century. These are high-energy particles that arrive at the Earth from various sources, some of which we're still trying to figure out. Once they get to the Earth, they are high-energy particles. They hit the atmosphere. The atmosphere is stuff as opposed to vacuum. So once the particles hit the atmosphere, they interact and they produce these very large showers of high-energy particles. Okay, that's supposed to be what that cartoon on the right-hand side is. Forget about the rectangles. They're different types of particles. One of the particles that is produced in these cosmic ray showers is a particle which many of you may not have heard of, a particle called a muon. It's like a heavy electron. You've all heard of electrons. A muon is like a heavy version of an electron. It's more heavy, has more mass, and it has one other important characteristic. Unlike electrons, it's not stable. So if you take an electron and look at it for a while, it just stays the same. In fact, it will stay the same forever, roughly speaking. A muon, that's not true of. It has a natural lifetime in its reference frame, when it's at rest, of 2 microseconds, roughly. 2 millionths of a second. So if I gave you a muon to look at, you'd only have 2 millionths of a second before it disappeared and produced some other things. So it turns out this was a little bit of a puzzle early on, because it was first observed, or when the cosmic rays were first observed, it became apparent that these particles called muons were being produced in these cosmic rays, cosmic ray interactions. And the puzzle was, how is it possible for muons that are produced, let's say 10 miles up in the atmosphere when these cosmic rays hit, how is it possible that they would make it all the way to the Earth's surface, which they do? And in fact, right now, you're being bathed in this sort of stuff, including cosmic ray muons that come from interactions of particles in the atmosphere. You can build, and in fact we have one through the door there, a simple detector that shows these particles passing through us right now. So how do they get from 10 miles up in the atmosphere where they're formed to the Earth's surface if they only live for 2 millionths of a second? Because if special relativity would not work, even if they're moving as fast as the speed of light, or close to, which they are, they would only travel for about half a kilometer before they disappear. Okay, so something is going on which allows them to travel all the way from the top of the atmosphere to the bottom of the atmosphere where we detect them. And of course what's going on is they're experiencing time dilation. So if we correctly interpret these with the Lorentz gamma factor that we just introduced, what you will find with the time dilation, the fact that moving objects, their clocks are moving slower, 2 microseconds for that fast-moving object is in fact, by our standards, by our clocks, much, much longer. And so if you correctly fold in the gamma factor, the Lorentz factor for something moving at 99.9% the speed of light, which roughly they are, they have a much longer lifetime. I multiply that by the speed that they're moving, and they can move about 15 kilometers before they disappear. That's about the distance from the top of the atmosphere to the bottom. So a very simple example, but, well, simple is a little bit esoteric, but simple example of time dilation at work. I'm not going to say anything about this. This area of cosmic ray physics turns out to be an active area of research for a variety of reasons, and people make use of this time dilation all the time when they do experiments to try and measure cosmic rays. Okay, so let me just close out. I'm going to post this with the correct font rendering online. I'm going to ask you, because I didn't get quite as far as I wanted to, namely I didn't get talk about length contraction or the Lorentz transformations. I'm going to post this online if you can. Just take a little bit of time to read a few slides ahead so that we can get started kind of right here on Thursday. Okay, that's it. Those of you who came late, make sure you've taken a look at all of the announcements on the chalkboard.
Oh yeah, no.
Any of you who handed in a midterm 2, purely only for looking at the second problem, with energy conservation, with strength of year, anyone else had a request that will return on Thursday.
Wow, what's your school again? Like a textbook? Oh, in middle school we didn't talk about matrix cube at all. In high school we did.
Because I was thinking,
Algebra 2 was like all over.
Not for me. It was like logs and stuff.
So the YouTube